right, everybody, thanks for coming. It's early, 9 a.m. on Thursday morning. We have a good crowd, so we really appreciate it. And we figured that if we put the words machine learning in our title, we were guaranteed to have a good audience, even though it's early, even though it's Thursday. So thanks for coming. Actually, the joke is on everybody. There's nothing about machine learning in this talk. That was just a ruse to get everybody to come in the room. So sorry to disappoint you, but no, this actually will be about machine learning. My name is Art Sadovsky. I'm a lead program manager in Microsoft Office 365 Security. I'm here with my colleague, Kevin Lowe, and we're going to be talking about how we use machine learning in our service to solve some of our most important security challenges. So there's a few things that I want to emphasize here. Our team focuses on infrastructure security. This is really the back end that powers some of our highest scale services in Microsoft. One of the reasons we wanted to give you this talk is because most of the time our customers or end users, they don't really have a great view into what we're doing on the back end. Right? If we're doing our jobs, they shouldn't have a good view into it. And yet at the same time, we want to make sure you're aware that we take this very seriously. We invest very heavily into securing the back-end infrastructure that powers our service. So even though you don't directly see the benefits of that, we want to make sure you're aware of what that level of investment is, what those outcomes are, what value that you get as a customer or prospective customer by moving to our service. We want to make sure you're aware of how strongly we invest in securing our infrastructure. And so we're going to talk about how we use machine learning to solve some very concrete problems. So just to be clear, this is not going to be an abstract or theoretical talk. We will be focusing on how we use machine learning in our production environments to solve some very specific challenges when it comes to the infrastructure monitoring space. And at the end of the day, we hope you have a few takeaways from this. Number one, as I said, we at Microsoft invest very, very heavily in securing our own infrastructure. When you move to our cloud, you can rest assured that we deploy the most advanced state-of-the-art techniques to keep your data secure, in addition to traditional techniques. We don't over-index on anyone. Whatever we need to do, we will do to keep your data secure. This is really a behind-the-scenes view into what that is. All right, so let's talk about what our team does. So the focus here is going to be on security monitoring. And again, we are talking about monitoring our own backend infrastructure. All right, so you may have been at some other talks at Ignite where you've heard about monitoring and detections and so on for various customer-facing features, admin usage, strange logons from various unusual destinations, maybe indicating account compromise. Those are all very important. We certainly hope you're interested in those, and we encourage you to attend those talks and learn more about that. But this talk specifically is going to focus on what we do to monitor our own backend, what we do to monitor the infrastructure and the machines that power our service that hosts your data. When it comes to that kind of monitoring, we have two primary goals that we're going to talk about here. Right? At the end of the day, we're trying to accomplish one very specific thing. We're trying to make sure that if an attack happens against our backend infrastructure, we can catch and stop that attack before any data is actually harmed, before any data is compromised or stolen or things like that. And for us to accomplish those goals, there are two specific things that we're trying to index on when it comes to our alerts. The first is accuracy. Right? We cannot tolerate a situation in which we raise a very large number of alerts for issues that happen in our backend. We only have a finite number of people who can respond to those alerts. If our alerts are noisy or inaccurate or not very meaningful, no one's going to be able to take action in time to stop any prospective attacks. So we need our alerts to be very accurate. And the other variable we care about is speed. Again, if you look at our primary objective, it is not to just catch attackers. It is to stop attackers who may manage to get into our backend before they can damage any customer data. If we're going to do that, then we need to be fast. Some of you may have attended a talk that my manager Raji gave a few days ago. It's called Assume Breach. And she cited a very important statistic. The statistic she cited was that if you look at security breaches throughout the industry, the average time for an organization to detect a breach of their infrastructure is 197 days, 6 months. That's something that we cannot tolerate. That's something that we will not tolerate. Because if we wait that long, the risk to customer data is simply too large. We have to be able to act in real time, both to catch and to respond to the attacks that may happen against the infrastructure. So as we go on through this presentation, keep this in mind. These are the two primary variables that we're going to be talking about. When we talk about how we use machine learning, at least for the purposes of this talk, these are the specific things we'll be talking about. Those of you who are familiar with machine learning know that you can use it for various other purposes in a security context. But just to keep the focus here, we will be talking about monitoring, and we're going to be talking about how we make that monitoring accurate and how we make it fast. All right, before we go on into machine learning, I want to spend a little bit of time talking about our security monitoring technology and how that works. So again, remember, we are monitoring our backend service. We're monitoring our own machines, of which there are hundreds of thousands powering Microsoft 365. Those machines generate a very rich set of signals. A lot of different types of data that we use to build security monitoring algorithms. You see some of the data types on the left side of the screen over there. We use network data. We use ETW-based events that we generate. We use OS-level data. We use contextual data about our service, what kind of operator accounts we have, whether a given person is on call or on vacation or things of that nature. The point is there's a broad set of data sources that we use. We operate at very high scale. We're talking about millions of events across these data sources and across our service that get generated every single second. And again, if you were in the Assume Breach talk, one of the key points you heard was that scale is actually an advantage. And we use that to our advantage because scale gives us a diversity of signals. It allows us to build more robust algorithms, as you'll see in this talk. The point to emphasize here is that our scale is huge. We have a diverse set of signals that we generate. Like about millions of events per second across hundreds of thousands of machines. Our monitoring infrastructure processes those events, and it turns them into actionable alerts. And today we're going to talk about how that happens. So before we go on into the details of how the machine learning works and exactly what those algorithms are and things like that, I want to spend some time talking about why we even want to use machine learning for this, what kind of opportunities it gives us. We don't want to use machine learning for its own sake, right? And nor is it the only technique that we use. But there are specific reasons why we want to use it for our service. The first point to emphasize is that our service is very complex. It's very dynamic. I mentioned on the previous slide, we're talking on the order of hundreds of thousands of machines that power our infrastructure, generating millions of events per second. Not only that, there are changes happening to the service all the time. We have thousands of engineers who are constantly deploying new code, trying to test out new features, troubleshooting issues that may arise. So there's a lot of weird stuff going on as a result of that. And the reality, especially for those of you who have worked in security, will appreciate, is that whenever you have a system that is that dynamic, and you have a system that is that complex, and is changing so rapidly, all that weird stuff, a lot of it is going to look malicious. Right? There's so many things happening that it's difficult to separate out that noise, to say, okay, what is benign behavior that is just happening as a consequence of the service being run at such a high scale versus what is actually malicious. It is hard to accurately separate those things out and to do so quickly. If you look at other techniques that have been used by other organizations, in some cases they rely on a lot of manual analysis. They might have a lot of algorithms that attempt to denoise the data and then need someone to manually look at it, and therefore they compromise on the speed angle of things. In other cases, again, if you look at some of the historical breaches we've had with other organizations, other companies in the last few years, you'll see that a lot of noise just gets generated. And the result of that, because of how complex their systems are, is that the people who receive the alerts aren't able to effectively act on them because they're just too noisy. And what we use machine learning for is to solve that particular problem. It's to effectively denoise the data that gets generated in our service, which is very complex, which is very dynamic. Right? The system you saw on the previous slide takes in a huge quantity of data. That data is inherently noisy for the reasons that I mentioned. The machine learning algorithms effectively separate out the malicious signal from that noise in order to produce alerts for our security team that are accurate. We'll talk about what that means in a minute, and that are fast, and that are raised in real time. And again, the entire goal of that, the reason why that's so important, is because it allows us to achieve the goal that I talked about a couple of slides ago, which is to catch and stop attackers before they're actually able to damage any of our customer data. And with that, I'm going to hand it over to Kevin, who is going to talk in more detail about what this machine learning is that we actually use.
Thanks, sir. So how do we actually use machine learning on the back end? in order to catch attacks in real time and generate paging alerts so that we can create actionable data for our on-call engineers. I'll walk you through it. On the highest level, we use supervised learning on the back end. Now, supervised learning is basically pattern matching. What we have is we have rich labeled data coming in, and this labeled data is labeled to say what looks like an attack and what is not an attack. Then from there, we can take in this labeled data and train a model. This model infers patterns from the labeled data to recognize and discern what is an attack from what is not, based on the labels. Once we have a trained model, which has absorbed all those patterns, we can take that model and compare those patterns against real-time data coming in through our Vanquish pipeline, and then generate real-time results. The beauty of this model is that it's actually able to output a number between 0 and 1, representing its confidence in when a given set of signals matches an attack pattern. So you can see on the very bottom, we've outlined the steps that I just walked through. And the key here is that the labeled data that we're generating is constantly generated in our system. We have automated actual simulated attacks by working very closely with our pen test team, our red teams. For those of you who don't know what that is, it's a team of hackers who are hired by Microsoft who hack for good on our back end. And they actually create malware that is benign that we can automate on a regular basis to run against our infrastructure. So this automated attack simulation gives us rich signal that we can overlay against the benign data that, as Art mentioned, is constantly being created in our systems. And then just going through, model gets trained, model gets compared against real-time data, and then we create alerts. So now let's walk through each of those steps in more detail. So as I mentioned before, we work closely with our red teams and pen test teams to create what we call AttackBot. AttackBot is a set, you can think of it as a set of attack simulations that represent real-life attacks. These are things such as data exfiltration. These are things such as changing the firewall rule so that you can actually get your C2 connection out. These are things such as maybe calling China and establishing the C2 connection to China. All of these real scenarios are automated to run against our backend using our AttackBot infrastructure. And keep in mind that these are truly benign. These are, while I say that these are running against prod data and prod infrastructure, the scenarios themselves have been well designed such that if we are doing something like data exfiltration, what we do is we create a blank file and we'll try and exfiltrate that file. We are by no means exfiltrating customer data. So the key here is that we run it regularly because Office 365 is a constantly changing environment. So we need these signals overlaid against the changing benign background signals. And as you can see in the picture on the right, or left, your right, that's just a frequency chart of how frequently AttackBot is running in our system. We're getting it at least once an hour, new scenarios, new random scenarios being kicked off in random places within our environment. So first step, generate labeled data. Second step, train the model. The model that we use in Office 365 in prod is a random forest model. You can think of it as it creates many decision trees, and you can think of an individual decision tree as being basically the game 20 Questions. Has anybody played 20 Questions here when they were a kid? So think of a decision tree as basically asking the most granular questions first, or no, the most high-level questions first, and at each level, each node going down in the tree, it asks more and more granular questions until it can determine whether or not a specific set of signals represents an attack. So a random forest model creates multiple decision trees and takes the output or the mode of all these decision trees when making any one decision of whether or not something is an attack. Now, why do we use this model? This model offers us several advantages. Firstly, it's resistant to overfitting. This is a concern with decision trees. And what we don't want is we don't want a model that's only going to work for one scenario, or it's only going to work for a very specific day of exchange or office, depending on how the backend is behaving. We want a model that's robust. Second, we want a model that's highly scalable. As Art mentioned, we're working on the order of 300,000 machines here, which is millions and millions of signals a second. So we need a highly scalable model that can handle large volumes of data. But the third is the best point. So third, it's not a black box. Unlike neural nets, the beauty of a random forest model is that it's actually going to output the feature selection and associated weights that it used to make that classification. So when it actually tells us whether or not something is an attack, the beauty is that it's going to say, why does that look like an attack? What features did it use to determine whether or not something was an attack, right? And then from there, our operators can determine how legit that is from their perspective. And so you can see on the bottom, data coming in, multiple trees created. The model then takes the mode based on that decision, and that decision could be whether or not something's an attack. And the beauty is that it spits out the reasoning as well. So now that we've gone over both the data that we use to train the model and the model itself, now we can go over training. So as I mentioned before, we have a TACbot constantly generating these awesome malicious signals and labeled data. Here you can see a list of some of these signals that it generates. So PowerShell exploit method names, remote thread injection, service installed, a C2 has been spun up. These signals are then weighted by a TACbot, or are then weighted by our model. So they get fed into the random forest model. The random forest model discerns its pattern from the signals, figuring out which of those signals below are most valuable against the background noise and weighting them accordingly. And then on the very end, you can see it's actually created the model itself, showing all the different features or signals and associated weights, right? And that's the beauty of it. So then we can take that and compare it against real-time data. So here we have the actual model working in real time against signals within our environment. So as I mentioned, we use the TACbot data to train our model, but we also use it to validate our model. So old AttackBot runs can train the model. New random AttackBot runs should hopefully fire off alerts from this model. So on the top, what you can see is, as I mentioned before, AttackBot scenarios create multiple signals. PowerShell exploit method names, IOC IPs, C2s, that sort of stuff. Now, in real time, our model is comparing these signals, as well as the background data, against the patterns that it's able to recognize. And here you can see this is actually a copy of the email alert that we get and the paging alert. And it actually highlights which features have fired off and their associated weights. Now, if we just go and sum all of those, we get a score between 1 and 0, right? And what we're able to do from there is we're able to set a threshold from which we want to be paged. And once we set that threshold, anytime the model sees anything in prod data that's exceeding that threshold, our on-call engineers get paged within 15 minutes. So this is far, far faster than the order of 6 months that Art was mentioning earlier. We want actionable alerts in real time. And so this is exactly what our on-call engineer would get. And they would be able to see that C2s have spun up. They would be able to see that there's new process connections, and they would have a greater understanding of the scenario, and that would allow them to take action. So let's do a quick demo. Let's see how this actually works within our environment. It's just a slide demo. Just want it to be safe for this one. So from our command console, we can actually spin up an AttackBot instance. Here you can see we're creating an AttackBot agent workflow against a real prod machine. And we've just given the reason that this is a test run. So now, once we spun up that workflow, we can actually see from the AttackBot UI itself that in this scenario, we're trying to do a data exfiltration. It's going through all these different steps on its own side. This is from the red team's perspective. Now, these steps actually generate signal for us as blue teamers, as defenders. And so on the flop side, when we take those signals, they get compared to our machine learning model. You can see the highlighted signals actually are the ones that actually fired off for that specific scenario. You can see that the alert was raised within minutes of the attack, I think 13 to 15 minutes in this case. And you can see that this was actually run against our prod environment, right? And remember, as we said before, data exfiltration scenarios, we're creating our own file, our own blank file to exfiltrate. So don't you worry. So, one sec. So this is the exact kind of alert that we would get as on-call engineers. We want this data to be as actionable as possible, and we want this data to be real time because we want to take action to stop attacks in real time, as I mentioned. We don't want to be responding 6 months after the fact. We want to be responding while the attack is going on, and we want to block attackers, right? So in a data exfiltration scenario, data is being exfiltrated through a C2 channel to some sort of IP address. What we've created is we've created scalable, automated workflows that our on-call engineers can then use to block an attack. So given that attack, if this were a real-life scenario, our on-call engineers would then call another workflow called request remediation null route. They would input the target machine, and they would input the C2 IP, and then that workflow would run in real time to block that attack within seconds. And from there, the data exfiltration wouldn't succeed because there will be a null route blocking it on the host layer. So overall, we want to have labeled data coming in, but this labeled data allows us to recognize high-fidelity patterns that allow us to train a model. But our main goal for this model is to have these actionable alerts in real time so that we can take exactly these actions, right? We don't want it to be a black box. We want to know exactly what to remediate and when and where. Thanks. Now I'll hand it back to Art.
All right, thanks, Kevin. So we hope you all appreciated that demo that really tied everything together, sort of end to end. Kevin made a very important point near the end of that demo, which is that just raising the alert really isn't enough. I just want to reemphasize this point because you should think back to what we said is our main goal. The goal is to outright stop attackers before they're able to get to customer data, before they're able to damage customer data. And what Kevin's demo just showed is that this model allows us to do those things. It raises the alert quickly. The alert that gets raised has enough information to be actionable for our response teams. They know exactly what they need to do. In this case, they were given the specific attacker command and control IP that the malware was attempting to contact. That tells us what we need to block and allows us to trigger our workflows in real time. Again, that's what allows us to achieve that goal that we set out in the beginning of this presentation. So let's just go back to those things in a little bit more detail. Remember, we said that our two primary objectives that we're going to talk about today when it comes to security monitoring are accuracy of our alerts and speed of when the alerts get raised. And again, the reason these two things are so important is that because without them, if even one of those things fails, if even one of those variables is not present, we're not going to be able to achieve our goal. We cannot stop attacks if our alerts are not accurate, and we cannot stop attacks if our alerts are too slow. So let's talk about the specific outcomes we've achieved with the model that Kevin just described. Let's talk about accuracy first. The first thing to keep in mind is that we page our own team based on the alerts that get raised. And what do I mean by paging? I mean that we have a 24/7 on-call rotation that will get called and texted and bothered in various other ways whenever one of these alerts gets raised. And if that on-call fails to respond and they ignore the alert, then it gets escalated progressively all the way up to our VP and so on. And so the point is that we have skin in the game with these alerts, right? We have to respond to them. Even at 3 in the morning. I'm on call this week. I very well may get paged at 3 in the morning. It's possible if there's something that happens that requires my attention. And the reason that's important is that you need to be aware that we stand behind these models. We cannot ignore these alerts because we page on them. Because we ensure that our on-call engineers who are on call 24/7 any time of day, when our real-time systems detect that something happens, will actually get the alerts and respond to them. That's how you know we take these things seriously. That's how you know that they're accurate enough. If they weren't accurate, we couldn't tolerate that. No team can survive if we're paging ourselves 20 times a day for false positives. Right? So paging is sort of the test that we use to know that these alerts are real, that they're accurate, and they're things that we want to be taking action against. Kevin also made a very important point when he explained why we want to use sort of a random forest model and one of the advantages of that. And the point he made was that it's resistant to overfitting. Sometimes you'll see when people use machine learning for these types of scenarios, they build a model that is very good at detecting one specific thing, but it's not robust. Right? And when you deploy it to production, it's not really able to do anything other than catch that one thing because it isn't able to generalize beyond that. So even though we train our models, and even though we validate our models periodically on the attack bot data that gets generated automatically and at scale all the time, we have other ways of testing our models to make sure that they work. Kevin mentioned that we have a very good red team in Microsoft. Very smart guys, very good hackers. Thankfully, they're on our side. And in addition to building attack bot, they will periodically launch unscheduled exercises where we don't know in advance that they're going to do anything. And they do some complex things, maybe things that they haven't done before. And then the test of our model becomes, hey, can we actually catch those things, even though we haven't seen them before? They bear some resemblance to what we see with AttackBot. That's ultimately what supervised learning is about, but they're not the same thing. And really, that allows us to say that our models generalize the things that we see in AttackBot. We aren't over-indexed. We aren't over-fitted on AttackBot. We can actually catch things other than that as well. And that's a very important test to make sure that these models are robust and they would actually catch attackers if any real attackers were to get into the system. So those are 2 important points with accuracy to keep in mind. The other thing to keep in mind is what we've already talked about, which is actionability. Right? We don't want these alerts to be a black box. Again, going back to the goal that we set in the beginning, to catch and stop attackers, we need to know what to do next when the alert is raised. Just saying that, hey, our system is very smart and saw something bad happening to this machine, that's it, that's not good enough because we don't know what to do next at that point. We certainly can't build any kind of automation based on that. If you're going to build automation and automatic response, you need to know things about what caused us to conclude that this piece of infrastructure was compromised. You need to know things like, what is the malicious outbound IP that the attacker was trying to communicate with? You need to know about which process the attacker was using on the machine. What are these data points that caused our model to conclude that this was actually malicious? And how do we translate that into action? Right? And so that's another angle of accuracy that these models provide. They're not a black box. They tell us what were the reasons why we concluded that this thing was malicious, and what can we do next? And you saw the remediation in Kevin's demo, where right after the alert is raised, we can trigger that action that will block connections to that C2 and prevent the attacker from stealing that data. The other angle that we talked about when we evaluate these alerts is timeliness, is speed. How fast are the alerts raised? So once again, I will just cite that statistic, 197 days. That is the average time that organizations take to detect breach against their infrastructure. And that is just not acceptable for us. We will not tolerate that kind of timeline for responding to threats against the infrastructure that hosts our customers' data. And so this alert that you saw gets raised within 15 minutes. We have real-time systems. And again, just as we said in the beginning of this presentation, the machine learning alerts are not the only ones that we raise. We have other types of alerts based on static rules and so on that we will also raise in real time, also with paging in some cases. But the point is, these alerts get raised in near real time. That is critical for making sure that we can actually take some sort of action to remediate the attack. Right? If you look at other organizations, as I mentioned, some of them may have alerting, but they require a lot of manual investigation. One thing that's common in the industry is anomaly detection, anomaly modeling, where organizations will raise or produce a list of things that seem suspicious, and then they expect their on-calls or their response teams to manually search through those and try to figure out which of those things are actually bad. Again, that's not good enough. We need our systems to do that for us because we cannot wait hours or days for people to evaluate these things and figure out which of them are actually bad. And so as you saw, the alert in this demo and in our production environments, they're raised in 15 minutes or less. The other thing to keep in mind is that the models themselves that are used to generate these alerts, they get raised or they get retrained regularly. I mentioned in the beginning of the presentation that the environment itself, that powers Office 360, the Microsoft 365, is very dynamic. There's a lot of changes that go on all the time. New code gets deployed, new features get built, people are troubleshooting, new capacity gets added, and so on. We don't want the model to only work against one particular instance of that environment. We need the model itself to be able to adapt to those environmental changes, to make sure that even as the environment grows, even as the environment itself that we're monitoring changes, the models themselves can keep pace with that. And that even when the environments themselves change, we can still be confident that we're going to catch the attackers that operate against those new versions of that environment. And what you saw in Kevin's slides is that, in fact, we do that. We regularly retrain the model. We don't just build one model, deploy, then forget about it. We're running AttackBot all the time against the environment, every single hour, with randomized scenarios, with randomized target selection. We're feeding that data into models that get retrained all the time to make sure that they are able to stay up to date with those environmental changes. All right. And so just to summarize, we want you guys to come away with a few important pieces of information. Hope you remember these things. The first is that we take infrastructure security very, very seriously. This is not something that you as customers or prospective customers get a chance to see too often, because this is really on our back end. These aren't customer-facing things, but we want to make sure you're aware of how seriously we take this, of how strongly we invest in this kind of stuff. This is just one example of what we do. We do a lot more work on the infrastructure security side, but we hope that this gives you guys the right impression that we take this very, very seriously. And when it comes to security monitoring in particular, which is the focus of this talk, we invest in state-of-the-art techniques, in addition to others. I don't want to make it seem like the only thing we do is machine learning and we ignore everything else. We'll use whatever methods we need to use to secure customer data, to make sure that we can catch attackers as quickly as possible and stop them as quickly as possible. We found that machine learning happens to be very effective at certain specific things, which you've described here, and we use it for those purposes, and we will continue using it for those purposes. And we will continue to invest in this, continue to push the envelope, continue to innovate in this space to keep your customer data secure. That's it. So we hope everybody enjoyed the talk. We have a few minutes left for questions, if anybody has any.
Hey.
Alex Romanza from Contiva. So, are you guys going to share your models at some point?
No.
Okay.
This model runs on our back end. It's proprietary. The use of it and in conjunction with AttackBot, overall, the entire system is proprietary. But in a sense, we are sharing it. This is running and protecting customer data real time, but it is exclusively for the Office backend.
Oh, okay.
Yeah.
That's right. Yeah.
Not for on-prem.
That's right. So yeah, Kevin's right. Just to reiterate that point, this particular model is something we use just for our internal services. There is no plan to open source it or share it at this time. beyond what we've
Because
discussed
the
here.
scenario should be the same, right, for any other organizations.
Potentially. The important thing to keep in mind is that a lot of the aspects of the model are tuned to the specifics of our environment. So by sharing that, we would potentially reveal certain things that we don't necessarily want to reveal. That's the main thing that we're concerned with.
We have a parallel infrastructure for the customer facing
Yes.
stuff. So when it comes to that, those things we would share. The things that Art and Kevin today talked about is totally first.
That's right. What you said is it's a very valid point. That in theory, a lot of these scenarios, the attack scenarios, are things that customers could care about. And there are, in the future, potentially going to be cases where we can not share the exact model, but at least talk about the general techniques or provide some ability for customers to use something like this against those scenarios. It wouldn't be the exact thing, though.
We have 200,000 Windows clients and
Yeah,
Yeah.
10,000 servers.
yeah,
And we have all the data in OMS already. So
yeah.
basically, we just need the model. And okay, thank you.
Yeah.
Yeah.
Thank you.
Thanks.
Yep.
Is there any plan to, share the pretend model that we can use in our environment?
So I think that
That's a similar.
yeah. So the question was similar. It's okay? Well, it's a very valid question, and for people listening on the call, on the video, the question was: are there plans to share sort of this model for customers to use? And the answer is sort of yes and no. The specific model that we talked about here, in many ways, is very much customized to our environment, so we can't just share that without revealing certain things about our environment that we don't want to reveal. But at the same time, we recognize that customers also would benefit from these things. They would benefit from being able to detect these attack scenarios. And so at some point in the future, it might be the case where we think about how we can offer a model like this, stripped of any service-specific details, to customers. There's no immediate plan to do that, but it's something we're definitely thinking about as well.
Okay, and you also mentioned that you use random forest because the chances of overfitting is low, right? As per my understanding, normally if the model is not generic enough and it has not the data is unseen, the chances of overfitting is more because you are trying to raise your accuracy rate and overfitting the model, and you're not worried about the precisions. So that's, is it a generic, I'm not from a statistics background, but is it a generic, thing that, you should use the random forest if you are, trying to avoid the overfitting?
So you can think of overall, machine learning is like a toolkit, right? Different tools perform better, different models perform better for different applications. In our case, random forest is good because when compared to certain other models actually have more of a tendency to overfit. So if you take an individual decision tree or a Bayesian classifier on its own, then there is more of a potential to overfit. Of course, then if you go on the other end of the spectrum, you could pick something like a neural net that can potentially be more a bit generalizable, but then you get into a black box scenario, right? You lose that selection of features and weights and stuff like that, right? So in our case, we picked random forest because out of our potential options, it seemed to be the least possible to overfit, the most scalable, but at the same time, we really wanted that feature selection. We didn't want it to be a black box, right? As with neural nets and stuff like that, which in their case as well are much harder to implement and maintain from an engineering standpoint, right? Random forest is a pretty simple model, comes out of box in many cases, right? Our secret sauce here is the fact that we have the automated attack bot runs that show our model what attacks look like against the background of the environment.
Got it. Okay.
Yeah, I think one of the key points that Kevin just mentioned was that at the end of the day, when we choose which model to use, we have to evaluate a few different variables and trade-offs, right? We want two things to really happen. Yes, we want to avoid overfitting, but B, we also want to make sure that it's not a black box, that we do have feature selection. So certainly overfitting is a concern, and Kevin explained how the model can help overcome that. On the topic of overfitting, one other thing I want to mention is that AttackBot itself has randomization built in, right? That's another thing that allows us to sort of mitigate the risk of overfitting on one specific scenario. There are some particular attack scenarios that AttackBot simulates, but even within those scenarios, there's a lot of variability.
Yeah.
And how it attacks the environment also has some variability built into it. So that's another tactic that we use to sort of avoid the risk of overfitting.
Thank you, guys.
Yeah.
Where do we go to start to learn how to build our own attack bot?
You got to be really good friends with hackers.
Not really. At some point of time, we may be thinking about giving an attack tool. So we have currently a tool in E5 called Attack Simulator, using which you would be, currently we ship 3 attacks on that. The password spray, phishing, and the dictionary attack. You'd be able to attack yourself and figure out the security profile. And we'll be developing more on that, and there was an ask from people, they wanted to be a developer platform model so that the customers can contribute. We are thinking about that too. So there is a version of attack bot for you. It's called Attack Simulator.
Given the other layers of security, how many of the attacks you see are by attack bot, and how many are actual attacks on your infrastructure? Is there a ratio there? And then, do you treat that data differently in your process?
So the first answer to that question is that we do not see attacks directly against the infrastructure right now, right? If we're to be blunt, we have attack bot, we have pen testers. We don't see attacks from external actors directly against our infrastructure. We certainly hope that never happens. The reason for these investments is to protect against that situation, but that has not happened. However, your question about what other ways we influence the model is very important, and I would say that we have a few other means by which we add label data or inputs into the model beyond attack bot. The first is the manual pen tests. Those happen all the time. Right? In addition to attack bot running automatically, we have our team of hackers that come in and simulate what an adversary would do in various complex ways. We can label that data manually to say, hey, this particular set of activity was actually a pen test. That then also gets fed into the model in addition to attack bot. We also have our operators labeling non-attack data as benign. And that gets fed into the model too. And that's important as well for that goal of differentiating attacks from non-attacks. And that's a huge set, as you can imagine. Given how big the service is, given how much stuff is going on, we regularly have people indicate whether something is benign or is attack bot or is pen test.
To add to Art's point as well, our on-call engineers will label what is benign, but in some cases they'll actually label what is really, really poor practice on some engineers' parts, right? If they're doing something that is way out of the norm. So we're able to add that as data into our model as well. And in addition to that, I think what you're getting at is the sheer amount of noise that we have in our system compared to the sheer amount of true positive signal is a very high ratio, right? So we use bootstrapping to increase the amount of true positive signal that we have, basically replicating the signal over top of the benign signal to get a higher ratio. What that ratio is right now, it varies. It varies month by month.
Thank you.
Thanks.
Yeah.
How many examples do you use to train and retrain your model?
There's 39 individual attack bot scenarios at any one time. These scenarios are run hourly on a random basis. So
Is it across the whole infrastructure
yes.
of the world?
Yes.
Yes.
Yes. Yeah.
Yes. So there's randomization both in terms of the scenario that gets chosen in a given hour, how that scenario gets executed, and which particular piece of the infrastructure gets targeted. So we will target everything we have worldwide.
And I came in a little late. Maybe you talked about it. But how many, initially when you were training the model, how many examples of feature data do you have for training the model?
What do you mean?
So the number of examples you used to train the model initially.
You mean the number of labeled examples that we used to train the very first model? That's cool. I don't think we have an exact number for you. We certainly ran AttackBot for quite a bit of time before building the initial model. So I don't have an exact number for you in terms of how many data points there were, but it was a substantial amount. Again, to make sure that we don't overfit on that, to make sure that we represent the full environment and things like that.
Cool.
All right, thanks everybody.